Yeah, hi guys. Once again, welcome back to this King class of operating system concepts. Now, going on to the topic. Okay, let's see something about like the topic we are going to see something is about process types and management. And this is the first part of the preceding part that we will be doing later on, right? So, before going to the topics, now let's see on through the thoughts of today, okay, as something that is out of the context, but and the thought for today is like the difference between the engineer and the doctor. Okay, so if you see the difference is like if engineers make a mistake, so it's seen by all the people. Okay, for many centuries, like the Leaning Tower of Pisa or something like this. Whereas if the doctors they do make a mistake, it is buried 6 feet under the ground. So this was the thought for today. And with this thought, now let's start the session. Okay, so what is the algorithm then? In the algorithm, it's like the algorithm is something like a formal expression or something not a formal expression. You can think of it as a logical procedure. Okay, and a logical procedure for what? And the the idea is like logical procedure for solving a problem. So any kind of problem, for solving any kind of problem, you can define some particular steps, and this kind of steps can be something very logical. And this kind of logical steps are defined as a algorithm, and they are very logical, and they are in a procedure. Okay, so they are to be followed step by step. Okay, so this is the idea behind it. Now, what is a program then? Program is something like a formal expression of algorithms by means of programming language, right? So a programming, so whatever that you defined before, like the logical procedure that you defined before, can be written in a formal expression. A formal means something that is syntactically correct. Okay, something like in a C programming language, right? So something like this. So a program is something that is that you formally express in a syntax. Okay, the algorithm. Now, programming language can needs a runtime support, and runtime support means having environment that have a compiler, debugger, okay, and the editor. So the most like the example of a runtime environment is a code blogger. Okay, what is a process concept then? A process concept is something like a sequence of operation performed by a program while executing on a given set of input data. So the data is inputted, and you have a sequence of operations. Okay, that must be performed by the program. That you syntactically you define the algorithm. That the algorithm you write that you design to solve a problem must be syntactically written, and this is run by a runtime environment. And the sequence of operations that the program performs to perform to solve the problem is quoted as a process, and this is the concept of the process, right? And the process includes something like a program counter, stack, and data sections, right? So now, going on through the process, we have two most important kind of process, that is a sequential process and it's like a state, it is not shared. Okay, so the state of a sequential process is not shared by any other process. That means it is something that is an independent process, and it is the result of this process is deterministic. Okay, it always depends on the input. The result of execution always depends on the input state, and whatever state that you input. Now its execution is reproducible. Given the set of input data, it always produces the same output independently. From start execution time, the execution speed, and the number of active processes on the same system, like something like this. So its execution can be stopped and restarted. So a sequential process can be executed, whereas it can be stopped, and at the same time it can be also restarted, okay, without causing any kind of ill effects. That means no harm is done in the process while executing. So if you perform such kind of stopping and restarting the process, right? Now going on to the next question, that is a concurrent process. A concurrent process is something that is very different from a sequential process. That is, it is very non-deterministic. Okay, its execution is non-deterministic. That is, the result of the execution depends on the relative execution sequence and cannot be predicted anything in advance. So it is totally non-deterministic. Okay, the execution is irreproducible. Okay, the result cannot be produced. Okay, it cannot be reproduced. It is not deterministic. So these are the key concepts that you have to understand in concurrent process. Many processes running on cooperation with other processes. So this is the idea of concurrent process. And this kind of process will be following, like we will be following this kind of concurrent process in the upcoming lectures, and it is one of the most important process that is being used. Okay, now there is a representation of this kind of process. This can be represented in a graphical form, and this kind of graphical form is called precedence graph, right? So a precedence graph is a directed acyclic graph, okay, whose nodes correspond to the individual statements, right? It shows in order in which the activities can execute. Like I said, the execution procedure, okay, on the basis of the execution procedure it is executed, right? So process 0, like SO, S1, S2, S3, S4, some such like this. Process 0, then process 1, 2, 3, 4, step by step, and this is, it goes in a sequential form. Whereas for the precedence graph for the concurrent process is something like this. That is, S0 will be followed by parallelly by S1, S2, S3, and parallelly to Sn, and the output result is executed here. Okay, it's obtained here, and it is non-deterministic. Now, what is the process state and process state diagram then? The process state is something like a process that acquires certain position, okay, and process can execute acquire many kind of state, many position, okay, something like as a process executes, it changes the state, it changes the position, and the state of a process means current activity in which the process is running. Okay, so there are 5 possible states a process can be in. It is like, first is new state. In a new state, a process is being created, whereas in the ready state, the process is waiting to be assigned to the processor. Okay, ready processor allocated to them by the operating system so that they can run. That means in a ready state, processes are allocated. Okay, so all the process, the operating system resources are allocated in a ready state, and then it goes to a running state. That means the process is currently being executed. Okay, whereas waiting state is something that the process is waiting for some events to occur. That means after the completion of a IO operation, that means after running state, the process wait for the IO execution operation. And lastly, after the IO input and output operation is performed, then the process, when the process is finished, it is done with its job, then the process terminates and it goes to the terminated state. That is, the process has finished execution. Right? And you can see here in a diagram, the state diagram of a process. It's like new, then it goes to the ready, then the running state. And also you have to understand is that like while the process is in running state, it can be interrupted, and after interruption the process again goes back to the ready state to wait for the allocation of the process. Okay, and after the process get allocated, it goes again to the running state. Then in the running state the process is currently it will be executed. Okay, and then similarly it starts waiting for the IO operation, then lastly it gets terminated. Okay, IO events or IO or event completion. Then after waiting state, the IO can still come back to the ready state. Even after the IO is like after waiting for IO, when the IO gets completed, it can again go back to the ready state and then waits for the process to get allocated and can again come back to the running state. Because this kind of process are done, for example, if you are doing some process for a long time processes. Okay, for example, if you are watching a movie, then it is this kind of process must be keep on the process has to keep on allocated. Okay, and it keeps on running, right? Some long-term processes are they keep on going back to the ready state, then the running state, then again wait, running, ready. Okay, unless it gets terminated. So this is the situation. Now, okay, about the question is about the process control block. In the process control block, that is PCB, what is it is like it is a data structure, and it is mostly used by the operating system to represent each process in operating system. That is, it contains a very important piece of information associated with the process, and this kind of information are, in the first is called pointer. Pointer is something, it points to another process control block. That is, each process has a process control block. So something like a process containing a process control block that is containing a pointer points to the another process control block of another process, and it is mostly used for maintaining scheduling list, right? So the second piece of information that is in process control block is called a process state. And as I have already discussed before, the state of a process can be in 5 different possible forms. So it can be anything, like it can be in new state, or either it can be in ready state, or it can be in a running state, waiting state, or lastly the terminated state. Now we have the program counter in a PCB. Then in program counter, what it does is like it indicates the address of the next instruction to be executed. To be executed for this kind of process. Now CPU registers are there, which totally depends on your computer architecture. So you can have like general purpose register or stack registers and type of register, totally that is depending on your computer architecture, right? Now for memory management information, we can have some informations that are the information that includes the value of the base and limit registers, the page tables and segment tables, depending on the memory system, okay, that you are using, okay, in the operating system. and this is usually for also most importantly used for deallocating the memory when the process terminates. And lastly, the accounting information is the information that is usually used for to do statistics. Okay, and it consists of so many things like time limit, job or process number, so many things like real time used, okay, how many times it's used, how many time limits is provided, account numbers, everything like that. And now is like what is it? Context switching. In context switching, we have a CPU switch. It's like we have a CPU that switch from one process to another process. It's like it is switching. The process is switching from one process to another process. So the process stop working in one process and start working in a second process. So this is something like switching. When CPU switches to another process, the system must save the state. Okay, in a process control, like the state, each process consists of a process control block, right? And process control block consists of all kind of information. So, and also most important idea you have to understand is like the state must be saved. Why the state must be saved? Because if a CPU, if the state is not saved, then when the CPU comes back to the current process, then the CPU has to start it from again process. So while CPU switching, like the context switching, the switching of the process that is switching from must be switched, like it must be saved, and the process, the CPU where the process is going, the CPU is going switched to must be like updated. That means the old state of the new process that is going to switch must be updated. That means it's loaded. The old process that was in the new process that is going to must be loaded, whereas the old process that it is leaving, the CPU is leaving the process, and it leaves only after it saves the state of the process, then it goes to the new process and loads the state, the saved state of that new process. And the time devoted for context switching is oftenly called overhead, and this kind of work is not directly useful for any kind of process, and so context switching time must be minimum. It must be very minimum to avoid such kind of overhead. Okay, now lastly in this kind of thing, like types of schedulers. Okay, what is schedulers? Schedulers are something that are used to do process scheduling, and mostly we have three kind of important scheduling, that is long-term scheduling, short-term scheduling, and medium-term scheduling. Long-term scheduling are something that are also quoted as a job scheduler. That means it selects which process should be called into a ready queue. That means it was already implemented here, like long-term scheduling. If the progress, like this process that is waiting for IO event, okay, this is waiting, and this is brought to the ready queue of a ready state, then this is called long-term scheduling. And short-term scheduling is like CPU scheduling that selects which process should be executed next and allocates CPU. That is involved very frequently and so must be very slow. So which process should be executed next and allocates to CPU. So that means it is also in the ready state, and which process must be allocated and must go to the running state is done by this short-term scheduling here. It's also a CPU scheduler. And lastly, a medium-term scheduler, which is mostly useful in a multi-programming, and this is it for the scheduler. Now the question is like, how do we create the processes then? processes are something that we are discussing here about. And parent process, usually what it is done is like a parent process creates a children process, child process, so which in turn creates other processes. That means a parent is creating children processes, and these children processes, being a parent, can also create other children processes, and they form such kind of trees of processes. Okay. So the parent and children can share all the resources. Okay, while creating the process, they can share all kind of resources, or children can share the subset of parents' resources, or the parent and child can share no resources, so they can live even without the resources, or they can share all the resources or some particular subset of the resources. For execution, the parent and children execute concurrently, that means in cooperation with one another, or the parent can wait until the child terminates by using a wait system call, right? Now the address space taken by the child is either the child is a duplicate of a parent, as a fork system call does the same. Like fork system call does is something like it creates a duplicate, identical duplicate of a parent process, or the child has a program loaded into it. So the child can already have a loaded program. That means you can use the exec system call, right? So by using the exec system call, you can directly load another new kind of program in a current program that is running on. Now let's go into the example. You can see the example here, like of fork. The first example is just about system call fork, and we can check out the example. We can also run it in our compiler like environment, like code, this code block environment. Now let's say this is the code, and if you try to run, you will see the fork system call that executes and creates some child processes. Okay, and lastly, you can also see that process 1 is here. You have to understand this kind of situation. And the parent process here, what is happening is something like it has printed out the statement. I am the parent, my PID is something, process ID is this one, and my parent process ID is this one. And this sentence has been printed by process this one, right? And lastly, the sentence is printed out and it gives the information about the process ID and the parent process of this process. 96 is something like a new child process that was created. And what is happening is like the child, the parent process executes before a child process finish execution. That's why the child here is becoming an orphan, and this is adopted by a root process that is a init process. So that's why the PID, the process ID of this parent process is 1, that is init process. You can see here, that is the reason why. Okay. Okay, giving you the idea, fork equals to 0 means fork returning a value that is 0, that means it is a child process that is inside a child block, whereas otherwise it is in a parent block. And in the parent block, it is already executing before the child. Okay, child gets forked, right? This is the reason why the child was orphaned, and then it was adopted by the init process. Yeah, this is all explained here. Now the second program is about a synchronous alarm program, and in this program what is done is like a simple alarm, synchronous alarm program, and this is just to display you about like a synchronous process, how the synchronous process occurs. And this while one means while always true, we print alarm and we try to read from the standard input. Okay. And whenever the string length, if the string length is less than or equals to 1, then it continues, and wherever it scans the particular for the particular information, and if it is less than 2, the information less than 2, then it prints out the standard error message, whereas it sleeps for the testing aligning given scanned seconds, and it prints out the information. So let's check out the program, and this is a synchronous program, and let's see how it is done. Okay, now we have to insert something. Let's sleep for 5 seconds. Let's print out the message, something like okay. So what it does, it will just sleep for 5 seconds, and it will print out the seconds that it has slept and the message, and along with the date. Okay, if you check out, yes, sleep seconds, right? The date is printed. Sleep seconds. The print out the particular seconds and the message, right? So see, this is done here, and this is a deterministic process. So whatever, and it is destined. That means whatever was printed here, I mean the result is determined, very deterministic. And all the properties of a synchronous process works here. And it works in a sequence because first it scanned, then it printed out, right? It didn't print out then scan. It was like it worked in a sequence. This is the idea. Now let's go to the third program that is designed in point of view to give you more information about like concurrent program. So it's just the same version of the alarm clock, but that is used in a concurrent way, like in a concurrent program. What is used is like we are using the include library that defines the process types. Okay, type for the process IDs and process group ID. So this is like include system types that h header file, whereas we also include the wait.h header file, which includes the system called waiting, and even we also include the errors.header file. These are mostly useful or has the definition for error exceptions. And you can check out here the program, and what is done in a program is like same the declaration, the variables, and then while it is true, what is done is similarly it does the following, the same scanning for the like reading from the input stream, standard input stream, then similarly it prints out the date, then else if it is not a bad command, then it checks out if it is child, parent or not child, and then similarly if you are in the child, you wait and then print the message, right? Similarly this thing is done here. Now let's go to the program and check out the situation. Let's close this previous program now. Okay, let's compile and run it. After compiling and run it, and the same information, like okay, let's wait for 4 seconds this time and print out the message. Okay, immediately it printed out the date, then waited for 4 seconds, then it printed out the message, the date, firstly the date, and then the respective message. That this is the child process that was running, that waited for 4 seconds and printed out the respective seconds, time, and the message. And this was to display the concurrent process, right? Now about generation of k children. That means we are trying to for k type k different children. That means the size k is defined here 3, and then we try to loop and for and try to check out for and try to print out the children, each children. And the most important thing you have to understand is each children has a different process ID. That means the child is independent of another new created child. Whereas also for the information, the index is also printed out. Okay, now for 3 was the situation. Let's close the previous program and let's compile and run this new program. And we see, yeah, and also for your kind information, this situation, the output can differ. It differs in different situations. Okay, if you compile different times, different result will occur. It does index 0, 1, 2 because for loop was from 0 to 3, so less than 3, so that is 0, 1, 2. First this child was created, and similarly the corresponding childs are created, and all these childs has become orphan because the parent process terminated before the child process were executed, and all these orphan childs will have their process ID like parent process ID 1. Okay, and for the explanation of how this process is executed is something like, firstly this child process will be created in a particular index, then each child process in this index number 0 will try to create 3 another child processes, okay, having same process ID but in a different index. And then the second child process will start creating 2 another child processes, new child processes with index 1 and 2, because index 0 it is in the first index, that's why the loop starts from index 1 here, and 2 here. Before loop started from 0 because this is from 0, this is the children with the index 0. Okay, this is a parent of index 0 that is creating these children, that's why it is starting from 3, starting from index 0. Whereas the third child process, process which will become parent process, and this will create another child process that will starting from index 2, because this is in index 2, right? Whereas if you go here, it will in this second index child process, it will create another child process that is with index 2, whereas because it has just only one index starting from 1, so only another one new child process can be created, whereas starting with index 2 it will create like 2 more new child processes. And similarly lastly this child process will be created, and the very lastly, like you have this only one new child process will be created with index 2. Okay, now in example 5, let's discuss about generation of k children processes. In this generation of k children processes, it is similar with the previous child process, but it is different from previous child processes, right? let's check out the example for 4K children. Let's close the previous program. Let's try to compile and run it. Yeah, we can see certain kinds of situation from index 0, 1, 2 with the respective parent process, like this is a process ID of children, and the parent ID has the same parent, and body of process with parent and the index 0, 3, 1, 2, right? Similarly, what is happening is like parent is 1. Also the situation is happening is because these 3 child process will be with the same PID will be created in a different index having the same parent ID, parent process ID. Then the body of process is this. In this situation, is the parent that is trying to print out first the parent and get the parent ID 68. Parent from index 0, 67 is another parent. 68. This process is 69, the new process, child process, with parent 68. You can see it, 68 was the child of process 67, right? 67 is creating 68, child 68, whereas like, and we can display here as a message like 69 is a child of process 68, whereas 68 is a process child 67, and then the respective index, and process 71 parent I, that means it is adopted by init process. With PID 1. Okay. Now the demonstration of a separate address space is presented here, and this is the last example program, and we can see here is this is just to illustrate the use of separate process address space with a common initial value. That means the two global variables, that is x and y, are declared. Then in the main function, what we do is we just try to initialize with certain value, and we try to create a children. In this inside a child block, we are initializing with another values, and we try to sleep, means wait for the child to complete. Then else, if it is this is in a parent block, okay, and either if it is in a child block, what happens is like we initialize with a different values. Y is initialized to -5, and then respectively we print out the values. So let's see the situation. This is the example, but let's go to the program and let's try to see like what is going on through this program. If you compile and run, you see certain kind of situation. It will wait for 4 seconds, okay, and then it will print out. I mean, it will sleep for 5 seconds, and then it will print out the respective message, and this was printed out. And this x and y is a global variable, and they are first in a child. Yeah, 24 was a child process. First the child process was created, and with the value that was initialized is 4 and 5, right? If you go and check out here, 4 and 5, and inside the 4 that's a parent that is inside is 5 and 15. 5 and 15, this is the parent that is with the process ID 23. Children, that is a process ID 24, 7, 9, 24, 7, 9, 23, right? And this is the respective thing. And this was all about like separate address space is allocated in case of child process and parent process. Now this was all about the first part of process creation and management. We will discuss about part 2, that is more about process creation and management. Okay, thank you for listening and see you in the next session.